Welcome back to Calculus 2. This is the first video for Chapter 5. This is Section 5.1. We're going to introduce sequences and series. Okay, so 5.1, we're going to go over the terminology of sequences. We'll look at taking limits of sequences. And we'll introduce an important theorem, the monotone convergence theorem. Let's start with terminology. To motivate sequences, let's look at an example due to Sierpinski. Take a square, any square. This one happens to be a unit square. Divide the square into 9 equally sized squares. Remove the middle square. This iteration is the first iteration, n equal 1. Now, we removed one of the 9 squares. There are 8 remaining squares. Repeat the process for each of the remaining 8 squares. And if you do that once and then 2 more times, so this is the n equal 3, then this is what would remain from the original square. Iterating once more for n equal 4, and again for n equal 5, produces something like this. This is termed the Sierpinski carpet, where we looked at equally subdivided portions and removed one of them. The process can also be applied for triangles, resulting in the Sierpinski triangle. And it is a motivation for sequences. For each n value that we had, we can look at the object that we have. When n was equal to 1, we removed 1 square, one of the 9. We can assign a number like the area that remains. And then on n equal 2, look at how much area remains, and so forth. Now, sequences in general are just an ordered list of numbers. We can denote that by looking at the first term, the second term, the third term, separating them out by commas. We can write down a sub n for the nth term. We can follow a sub n with an ellipses, indicating that this is a sequence of infinitely many terms. Other notation is to use curly braces. Curly braces would indicate a set. So we have a set of terms. The general term is a sub n. A sub n, the n is the index. And that we want to start with the first term and go out to infinity. So this is a much more compact notation. Write a few things down, that n is the index, and that a sub n represents the nth term of the sequence. Okay, good. Let's do an example. Let's suppose that we have an ordered list of numbers, i.e. a sequence, where the first term is 1, the second 1/2, the next 1/4, the next 1/8, and so forth. Then what we're doing is we're taking 1 as a sub n. We have 1/2 as a sub 2, 1/4 as a sub 3, 1/8 as a sub 4, comma, dot, 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 comma, and then the nth term. And this sequence goes out for infinity. All right, now we can do a simple analysis. We know that we can write down 1 equivalently in the form of 1 over 2 to the 0, that 1/2 is the same thing as 1 over 2 to the first, 1/4 is the same thing as 1 over 2 squared, 1/8 is 1 over 2 cubed. This then allows you to see a pattern in the denominators, which you can easily repeat to produce the next term. So the next term would be 1 over 2 to the 4, or 1 over 16. And 1 over 16 would be a sub 5. So when you're looking at the powers to the base 2, you want to relate it back to the index n. And you can see that the power is 1 less than the index. In other words, n minus 1. Thus, if you want to find the nth term in the sequence, in other words, the general term, you simply plug into this formula the expression 1 over base 2 raised to the index minus 1. Very good. So this is a sub n, the nth term, i.e. the general term of the sequence. So this expression entirely determines the sequence. Nice. So there are two basic sequences that you want to be familiar with. The first one is arithmetic. And arithmetic, what's a basic arithmetic operation? Addition. So what is the arithmetic sequence? Here we have two statements. These statements are determining a recurrence relation. So this arithmetic sequence is here defined recursively. Let's take a look. The first statement is telling you where to begin. It says start at A. In an arithmetic sequence, to move from term to term, you add in a common difference. Note that if we start at the first term and want to produce the second term, that means we're looking for a sub 2. 2 is the same thing as 1 plus 1. Let n equal 1. Then you can see that the second term is the first term plus the common difference. Then, if you want the third term, well, having knowledge of what the second term is, you're able to produce the third term. Good. So this second expression is a recursive definition for an arithmetic sequence. You need the recursive definition as well as where to start. Let's do an example. D is the common difference, and common in that for any successive terms, they differ by exactly D. That is the defining characteristic of an arithmetic sequence. All right, so an example. If you want to move from 2 to 5, or 5 to 8, or 8 to 11, and so forth, you are consistently adding in 3. Thus, the common difference here would be 3. Where did the sequence start? It started at a equal 2. Thus, the first term is a1 equal 2. And the recursive definition is that the next term is the current term plus the common difference, 3. Beautiful. If you wrote out a few of these terms, you could see that you're starting at 2, and then to move to the next term, you're adding 1, 3. But to move from the first term to the third term, you're adding in 2 copies of 3, and then 3 copies of 3 to get to 11, adding in 4 copies of 3 to get to 12, and so forth. So if you want the nth term, you add to 2, n minus 1, the index minus 1, copies of 3, the common difference. Nice. So the boxed quantity is the nth term expression, which entirely defines the arithmetic sequence without the need for 2 separate statements, like here in the recursive definition. Okay, so make sure that you're comfortable with arithmetic sequences. They're quite straightforward. You want to know the terminology. The second basic sequence is a geometric sequence. Here in Chapter 5, the geometric sequence will play a fundamental role. So make sure that you know the geometric sequence. Let's take a look at what it is. Just like the arithmetic sequence, we're going to start with the geometric sequence defined recursively. So you need a starting point, and then you need the recursive definition. In the arithmetic sequence, you would add. Here in the geometric sequence, you multiply. The arithmetic sequence, you added a common difference. Here in the geometric, we multiply by a value, and that we call that value the common ratio. Note that if you solve for r, that you get the next term divided by the current term. A ratio. Good. Here's an example. Let's say that we start at 2. Multiply by r to get 1. And then 1 multiplied by r producing a half tells you that r is 1/2. And indeed, a half times a half is a quarter. So the common ratio is r. And the starting point was 2. Thus, the recursive definition is the next term is the current term times 1/2. And note that the general term is the first term multiplied by r raised to the index minus 1. Similar to how in the arithmetic it was the first term plus the common difference taken n minus 1 times. Very nice. So again, here's an elementary assignment to make sure that you're comfortable with a geometric sequence. All right. So basic terminology of a sequence, it's an ordered list of terms. We want to do calculus. A fundamental notion in calculus is the idea of a limit. Let's look at taking limits of sequences. Okay. Given a sequence, if the terms an become arbitrarily close to a finite number, capital L, as the index becomes sufficiently large, we say the sequence is a convergent sequence, and capital L is the limit of the sequence. In this case, we write that the limit as n goes to infinity of an is L. On the other hand, if a sequence is not convergent, we say it is a divergent sequence. All right, so convergent and divergent. Now, remember in that definition, capital L is a finite number, a real number. Okay, let's do an example here. Consider the sequence a sub n given by a sub n, the general term, is 1. Okay. Now, let's employ some graphical representation. And here we're plotting terms of the sequence. So it stopped at 10, 1. The 10 is the index n. So we have 10, that's the index, and then we have 1, and then that's the value of the 10th term in the sequence. Well, all of these are occurring on the horizontal line, y = 1. So is it easy to project as you take indices higher and higher what the y coordinate of the dot is going to be? Yeah, they're all going to be 1. In other words, the limit of this sequence is 1. Pretty straightforward. All right, I referenced a horizontal line, y = 1. And that is what we want to look at in this theorem. If we have a sequence such that the terms of the sequence are the same as some function evaluated at the index, and if we know that that function limits to L as we look at inputs moving to the right, then we know that the sequence converges, and furthermore, the sequence converges to L. All right, let's try and digest that. We'll do an example. So here is a sequence. The general term, an, is 1 over the index. Now, a convenient trick is to just swap out the n for an x, and then think of, do I know the graph of this function? That would be 1 over x. Sure, that's the reciprocal function. So if we define f as 1 over x, then the nth term of the sequence is nothing other than the function f, the reciprocal function, evaluated at index n. Now, the benefit of doing this is that we could look then at the graph of the function f, the reciprocal function, the blue graph that we're looking at. And then when we look at red dots corresponding with terms of the sequence, they would all lie on the graph of f. And you can simply think of what is the behavior of the graph. In this case, the reciprocal function tends to 0. 1 over larger and larger goes to 0. And then that informs the limit of the sequence. We can see that the sequence is a converging sequence. All right. Very good. Let's do another example. Let's play around a little bit. So we had 1 over n. Let's look in the numerator, and let's force the numerator to ping pong back and forth, positive, negative, positive, negative. We can write out the first few terms. We know that we're going to get 1, a half, 1/3, 1/4. Oh, wait a minute. We need to ping pong. So that's -1, positive a half, -1/3, positive a fourth, ping ponging back and forth, positive, negative, positive. Graphing this out, notice that when we get the terms of the sequence follow two different curves, two blue curves. Both of the blue curves tend towards 0. Thus, this will also limit, this sequence also converges to 0. One more example. Now, let's watch a video on this one. If we take the sequence a sub n as -1 raised to the n, something that is always good to do is to start with the very first term, look at the next term, and repeat. So write down the first few terms, and then pause for a second and think, well, if I graphed these out, what would they look like? And we know that they're ping-ponging back and forth. Now, if we were to simply take the even indexed terms, they would all have an output of +1. Those even indexed terms limit to 1. Likewise, the odd indexed terms limit to -1. But that's not our sequence. Our sequence is the sequence which ping-pongs back and forth, and as such, it's not converging, it diverges. All right, so here are a few different sequences. You want to determine whether the sequence converges or diverges. If it converges, find the limit. So we had a theorem. If you were to replace out the n with an x, do you have a function for which you know the graph of? And can you take the limit as x's go out to infinity? If so, then you can easily determine convergence, divergence, as well as the limit. If not, then start with the first term, write down the second term, and see if you can observe any kind of pattern. Good. All right, moving on. Well, what if we have a sequence where the nth term is the index raised to 1 over the index? Okay, this is a little bit more complicated. We know that if we were to take the index out to infinity, then the form of the expression on the right, the form defining the general term, would take the form of infinity to the 0, which we know from Calculus 1 is an indeterminate form. In dealing with indeterminate forms, you know that your friend is L'Hopital's. But L'Hopital's is applicable when you have a quotient. Here we're looking at base to a power. Aha! The nice guy there is the natural log. The natural log has the power rule, so that if we take the natural log of the nth term, we have the natural log of a base to a power, and then that power can be brought out into the front. That's the power rule for logs. Thus, we're looking at a quotient, ln over n. The behavior of the natural log is to become large as input n becomes large. In other words, we have an indeterminate form, infinity over infinity, and thus we're able to apply L'Hopital's. Now, something strange, perhaps, is that n is discrete. It's only counting numbers. But if you recall that we can swap out for a function which has the same form, then we can apply the continuous limit, and L'Hopital's goes through nicely. Okay, so the derivative of n with respect to n is 1, and the derivative of ln is 1 over input, so we get 1 over input. What's happening with our input? It's going out to infinity. 1 over huge is very small, thus the limit is 0. But if you look closely, this is the limit not of an, but the limit of the natural log of an. We had to employ the natural log in order to access L'Hopital's. Now that we're done with L'Hopital's, we have to come back and clean up our reformulation of the problem. We clean up ln by removing ln through the exponential. Base e. We can use properties of limits to pass the limit into this continuous composition. And the limit of ln of a was 0, so we end up with the exponential of 0, or 1. Beautiful. Here are some other sequences to play around with. Determine whether the sequence converges or diverges, and if it converges, find the limit. Good. In Calculus 1, there was this notion of the squeeze theorem. Here, in sequences, that squeeze theorem may also be applied. Suppose that you have 3 different sequences: general term an, general term bn, general term cn. Looking further out into the sequence, suppose that the corresponding indexed terms always observed this continued inequality, that an is less than or equal bn, less than or equal cn, after some index. Next, suppose that the an's and the cn's are each convergent to the same limit L. So limit n goes to infinity of the an's equals the limit as n goes to infinity of the cn's. Again, remember that L is a finite value. The squeeze theorem then tells you that the bn's must also converge to the same limit capital L. Good. Let's do an example of that. All right. So this general term, the product of sine of n and sine of 1 over n, looks a little bit complicated. However, this is a sine function that we're working with, and we know that the output of sine is always between -1 and 1. So the nth term, defined as a product of sines, we can look at one of the sines, and we can estimate on the low side with a minus sign, and we can estimate sine of n on the high side with a +1. Doing so, we can remove that quantity and just be left with sine of 1 over n. Now, the insight and the reason why we're swapping that one out is because we know that 1 over n is going to tend to 0 as n gets big, and we know that sine of 0 is 0. All right, so what did we do? We wanted to remove this guy by saying that it can be no worse than -1 and no greater than +1, and thus we have a sequence on the left and a sequence on the right for which we know the limiting behavior, sine of 0. So sine of 0 is 0, thus plus or minus sine of 1 over n is going to tend to 0 as n goes to infinity. We have the required string of inequalities and the limit, thus the guy trapped in the middle must have the same limit. The ANs must tend towards 0, must converge to 0. Good. You give it a try. Apply the squeeze theorem. In applying the squeeze theorem, you need to show two different things: that the string of inequalities holds and that the limit of the left and rightmost sequences are the same finite value. Nice. So we've gone over the terminology of a sequence, an ordered list of terms, and we've looked at taking limits of sequences. We now want to talk about monotone convergence. All right, so here we're looking at the graph of a sequence. The general term of the sequence is 2 minus e raised to the negative 0.18 times the index n. Now, we know that the decay exponential is always less than 1 for positive inputs, and 2 minus 1 is positive. Thus, the nth term is always bigger than or equal to 0. So this guy 0 is something which is always smaller than the nth term. We can phrase that as the sequence is bounded below. Having an inequality as such allows us to state the sequence is bounded below. On the other hand, since we have the nth term as 2 minus a positive quantity, then the nth term will never exceed 2. In other words, this sequence is bounded above. The sequence is bounded above by 2, as the nth term is never bigger than 2. The nth term is less than or equal to 2. So what we have done is we've motivated the idea of bounded above, that a sequence is bounded above if you can find a real number m such that m is always bigger than or equal to the nth term of the sequence. Equally, a sequence is bounded below if you can find a real number m such that m is less than or equal to the nth term of the sequence. Now, we have these two notions, bounded above, bounded below. We can combine the two notions in a single term, bounded, if the sequence is both bounded above and bounded below. Sequences which are not bounded are termed unbounded. Good. So that's the notion of bounded. Now, you want to recall the nth term of a geometric sequence takes the form of the starting location a multiplied by the common ratio r raised to the index minus 1. And then you want to use that nth term form for determining if a sequence given by r to the n is bounded and whether it converges for these different values of r. Right? Good. Okay. Some more definitions. A sequence is increasing if the current term is less than or equal to the next term. Now, this needs to hold for all terms after some beginning index. So if after the 100th term, the next term is always bigger than or equal to the immediately preceding term, then the sequence is increasing. If you switch the inequality, turn it around, have it go the other direction, then instead of increasing, you would say that your sequence is decreasing. Good. Now, if your sequence increases, it's a monotone sequence. If your sequence decreases, it's a monotone sequence. We've looked earlier at the sequence where the general term is 1. Since our definition of increasing, decreasing allows for no change, a constant sequence is both increasing and decreasing. A constant sequence is monotone. There is no change. Monotone also speaks to it moves in one direction. It's moving up, increasing, or moving down, decreasing. So monotone is either increasing or decreasing, but it could be both. Monotone. Now, the monotone convergence theorem provides you with a condition for which you can conclude the sequence converges. What's needed in the monotone convergence theorem, the sequence must be bounded. Furthermore, the sequence must be monotone. All right, let's do some examples of MCT, the monotone convergence theorem. Let's say that we have a recursively defined sequence beginning at 2. And then for the successive term, that you take half of the current term and add to that 1 over 2 times the current term. All right, so we want to apply MCT, the monotone convergence theorem. 2 things are required in applying MCT. You need the sequence to be bounded, and you need it to be monotone. MCT, monotone convergence theorem. Well, where do we start? Okay, so a good place to start is to write down the first few terms. Try and investigate the sequence and see what's going on. So first term is 2. Next term would be you plug in the current value of 2, get 1 plus 1 over 4, that's 5/4. Repeat the process, get 41 over 40. So we had 2, we drop down to 5/4. It's about 1 1/4, that's 1 1/4. Then next one, 41 over 40, that's just slightly bigger than 1. 3,281 over 3,280. Well, that seems that there's a trend of decreasing. And because it's decreasing, it seems to be bounded above, but it also seems to be bounded below by 1. So just looking at the first few terms provides us with a guess that the sequence decreases and is bounded below by 1. Now, we're making a conjecture. We're guessing that this is the case. We now have to establish these 2 conditions. Decreasing, if we can show it's decreasing, then it's monotone. Bounded below, then we can establish that it's going to be bounded. We're going to go through this one by one. We'll start with the boundedness. All right, our conjecture is that it's bounded below by 1. What does that mean? Well, we can write down a statement that If the terms are bounded below by 1, then the sequence of next terms are also bounded below by 1. So write down that the next term is bigger than or equal to 1. And then use the recursive definition to express out the next term in terms of the current term. All right, so we need to establish this. So we have something to check off. So here's what we want to establish. We don't know that it's true. But note that we can combine these two terms, make a common denominator. First term is lacking a sub n in the denominator. That's going to give us an an squared in the top. And the second term has a good denominator. Okay. Algebra. Let's get rid of that denominator. So it pops up on the other side. We can then bring this right-hand side over to the left. We then have a quadratic expression in a quantity a sub n. And then the form is such that this is a binomial squared. It's the binomial a sub n minus 1, but you're quantity squaring it, and no matter what, since these are real numbers, when you square a value, you indeed will have something which is greater than or equal to 0. Thus, this is indeed true, which we may relate all the way back to our supposition. So we can now conclude that what we supposed, boundedness below by 1, is indeed true. So we are able to check off our box. Good. So we have boundedness. We want to apply MCT, the monotone convergence theorem. We next need the monotonicity. So, and from looking at the first few terms, we were concluding that it's a decreasing sequence. How can we establish that? All right, well, let's work with what we have. We have that the sequence is bounded below by 1. So that's this statement here. We can do algebra. We can square both sides. No problem. We can then add in a sub n squared on both sides. So we get 2 copies, and then we get the one that already exists, and then the a sub n quantity squared that we're adding in. And this we're able to manipulate. If we divide through by 2 times an, we'll be left with a single an on the left. And then on the right, thankfully, this one has been cooked up such that we have now reproduced a sub n plus 1 on the right-hand side of this greater than or equal to symbol, so that the current term is bigger than or equal to the next term, which is exactly the characteristic of a decreasing sequence. Voila. Beautiful. Fantastic. We thus proceed and claim our reward. 1 and 2 allows us to go by MCT. Monotone convergence theorem, we need boundedness, we need monotonicity, we have both. What does MCT give us? It gives us that this guy, the sequence recursively defined, has a limit. But if the sequence has a limit, then the limit of all next terms limits to the same thing. Good. So MCT brought us the first statement and then a simple analysis. Well, we can swap out the current terms with the next terms. They're going to have the same limit. And using that, we're now going to swap out the next term in its form. And now that we have this, what do we want to do? We want to use properties of limits. So here we're taking the limit of a sum which would be the sum of limits. But then the first guy is the limit of a term which moves over the limit of a constant. We can bring the constant out. And then when we're looking at limit as n goes to infinity of a sub n, we know that that's L. So wherever a n appears, applying the limit to it, we swap it out with an L. A n, push the limit onto it, and swap it out with an L. Well, well, well. What do we have? We have an opportunity to do algebra. All right, let's get rid of that denominator. Multiply both sides by 2L. Gets rid of the denominator. L goes to L squared. 1 goes to 1. L goes to 2L squared. Nice. Combine the L squared terms. Come up with L squared must be 1. But since the sequence is a sequence of non-negative terms, we know that the L must therefore be positive 1. All right. So we just did an example applying the monotone convergence theorem. To apply the monotone convergence theorem, you need 2 conditions satisfied: boundedness and monotonicity. After we established MCT, we were then able to apply MCT and do algebra in order to pin down a value for the limit. All right, so your turn, mimic what we did in that assignment. And that brings us to the end. Thank you so much for watching. Please like if this video is useful, and I will see you on the next one.